Okay, this question, we're going to find the area of a triangle using cross product. These are 3 points in 3 space. Okay, so just to get an idea of what we're talking about here, we'll quickly create a 3-space model. We have something that looks kind of like this. Okay, we'll try to plot all of these points here. First point is -1, 2, 1, so some point may be there. The next point is at -1, which is on the x-axis, and the final point is at 1, 2, 3, -1, and 4. Okay, so in 3 space, let's do different colors. So here's our first point. Here's our second point, or vector, I should say, not really point. And here's our third vector from the origin. Okay. But really what we need to do is we need to turn these 3 points into a triangle. So I like this color, so we're going to use that. Oh, that's not bright enough. We'll use red. Nope. Orange. Okay. So the orange is going to represent our triangle in 3 space here. So we have to create that triangle there. Now I know it's hard to conceptualize because it is on a 2-dimensional piece of paper, but the problem is with the parallelogram and the other things we used, we were always referred to the origin. Okay, vectors coming out of the origin. All 3 of these points are floating in 3 space. Okay, so in order to figure out the magnitudes of the vectors, okay, because we're using our vector cross product to figure out the area of this triangle. Remember, the cross product was vector A and vector B. And we actually have to find the magnitude of it and actually divide it by a half, because that will find a parallelogram, but it won't find a triangle, and a triangle is half a parallelogram, so we divide our final magnitude in half. So, in order to do this, what we're going to do is we're going to find the magnitude of each of the 3 new vectors. Okay? These vectors were all coming out of the origin. So if I called that vector A, B, and C, each of those vectors, the black one, red one, and blue one, all came from the origin. The orange vectors need to be renamed and resized. Okay? What we're going to do to find them is we're actually going to consider it, when we're doing cross product again, we're also referring to a specific point. It's essentially 2 vectors from one specific point. We don't actually make a triangle. So we have a point here, and usually called it O, and then maybe this one was A and this one was B, and they called this vector B and this vector A, let's say. Or maybe vice versa, who knows. But in order to do this, we have to have a point we're centered around. So what we're going to do in this question, in the book I think they centered around the letter A. Okay. So this was our A, B, and C. They're going to center around the letter A, and they're going to use the other vectors. So from A to C, that's going to be one of the vector lines, and the other vector line was going to be from A to B. So those are our 2 vector lines. So in other words, we're making 2 new vectors here. We're making vector AC, which we don't know the coordinates for, or we don't know the magnitude of, and direction. And we're making vector AB. Our connecting point is at point A, which would essentially be like this if we're in 2-dimensional space. So in order to do that, we actually have to find out what vector AB and AC are. In order to figure out vector AC itself, we need to subtract our vector A, or coordinates of A, from our coordinates of, well, in this case, they did B first. AB, we'll do AC first. So we take our x2, remember, minus x1, y2 minus y1, and in this case, z2 minus z1 to find out the magnitude or the distance of those lines. So since C is technically our second, this will be x2, y2, z2, and this will be x1, y1, z1. Okay? So we go to plug it into our formula to find out what AC is. Vector AC, the components of it are x2 minus x1, y2 minus y1, and z2 minus z1. Okay? I'm going to zoom in here because it's a little hard to see right now. So that's our formula to find out what vector AC is, or the component parts of this vector. So C, our x value was on the other page. Here we go. Our x value for C was 3, and our x value for A was -1. So 3 subtract -1. And then we have -1 subtract 2, and 4 subtract 1. Okay. From there we get 4, -3, and 3. Is that what they got on the other side? Yes, they did. So vector AC as the component value. So essentially what this is telling us, if we were to make a projection vector from the origin, it would go from the origin to these 3 points. Okay? That's the idea of that. And the idea for B, same thing. Vector B, same formula. I'm just going to actually, instead of writing the formula out since we already have it, I'm going to go straight to the points. The first point was -1 and A is -1. So -1 subtract -1. Then we have 0 subtract 2 and 0 subtract 1. So vector AB is equal to 0, -2, -1. Okay. So now we have our 2 parts, vector AC and vector AB. And I'm going to zoom out one more time just to try to make sense of this. So what I've just found is, and I'm going to rename it. I'm going to call this vector X and Y. Okay? This will be our vector X and this will be our vector Y. AC will be Y. So this is our vector Y and this is our vector X. We're then going to find the cross product of the 2 of these. So this was the extra step that we didn't do last time. We had to actually find out where these were in 3 space. Once we had their component vectors, or the projection vectors, sorry, we take those components to them, and then we're going to find the cross product. Now, I know a couple of you guys do it a different way. I'm going to follow the formula. If you have another way of doing it, there's nothing wrong with it, as long as you get the right answer while going through. So, entire page. Do you want me to write cross product formula again, or? Okay, you guys remember that formula from before? Well, okay, since it's technically a new recording, we're finding the cross product of X and Y. Okay. And again, we actually have to find the magnitude of it, but because we don't know the angle between these 2 vectors here, we're going to do it this way. We're going to find the cross product of it and then find the magnitude of X cross Y. So I will write the formula out. In this case, it would be technically x2 y3 minus x3 y2, x3 y1 minus x1 y3, and finally x1 y2 minus x2 y1. Okay, all referring to the 3 coordinates of x and y. So if these are our values, okay, let's make sense of it. X2, oh gosh, which one did I call x? This is, okay. -2 times 3, subtract -1 times -3. X3, -1 times 4 minus 0, well that's clearly going to be 0, times 3. And our last component part, x1, 0 times y2, -3, subtract -2 times 4. Okay, so we use all of them. Then we find our 3 components. This becomes -6, still minus 3. -4, subtract 0, 0 plus 8. We get -9, -4, and 8. Those are the cross products of that. And from there, we got to find the magnitude of it still. So the magnitude of x cross y is we use that little formula we have, square root. Should have been doing that from the start. Of -9 squared plus -4 squared plus 8 squared is equal to 81 plus 16 plus 64 all square rooted. See if we can figure this out. That'll be 70, 80, 161. Root 161. Are we done? Ooh, that's way too far. Are we done? Have we found the area of the triangle? Is it the cross product of those two? It's half of this. That's the area of the parallelogram. For the triangle, we'd have to multiply a half times the root of 161. Zoom out a little at a time here. No, I did that the opposite way. Oh, that doesn't make sense.